Our session today marks the beginning of a crucial area in engineering mechanics, stress in beams 1, specifically focusing on shearing force and bending moment. The concepts we cover today form the bedrock of structural design. A beam is fundamentally a structural element whose primary purpose is to carry loads applied transversely or perpendicular to its longitudinal axis. When we analyze these loads, we must first categorize the beam based on how it is supported. We identify two foundational types, the simple beam and the cantilever beam. A simple beam is characterized by supports at its ends, which allow it to span a distance. In contrast, a cantilever beam is fixed rigidly at one end, leaving the other end free. The specifics of the supports are paramount because they determine the reactions generated by the structure against the external loads. We examine three main categories: the pin support, that is simple support, and the roller support, and finally the fixed support. Understanding these support conditions is the essential first step, as accurately calculating the external reactions is a prerequisite for finding the internal forces. Let's delve deeper into the function of each support type. The distinction lies in the number of restraints imposed on movement. The pin support, this is a pin support. That it is also called simple support, is designed to prevent translation in both horizontal and vertical directions, but allows the beam end to rotate freely. Consequently, a pin support introduces two unknown reaction forces, Rx, reaction force in x direction, and Ry, reaction force in y direction. On the other hand, the roller support is less restrictive. It prevents only vertical movement. This means that the vertical movement is restricted, while allowing the beam to move horizontally and rotate. Thus, it provides only one vertical reaction force, Ry. Reaction force in y component only exists. This allowance for horizontal movement is important, as it prevents thermal expansion or contraction from inducing large unwanted internal stresses. So in this case, the horizontal movement is allowed when a temperature increase or rise is generated. It can expand in the direction of the axis of the beam. Finally, the fixed support is the most rigid for among the three. It prevents translation in both x and y direction. Look at this point. It prevents translation in both x and y directions, and crucially, it restricts rotation. Okay? Rotation of the beam is not allowed at this point, at the fixed support end, because it restricts all three potential movements to translations. Translation in x and y directions are prohibited, and also the rotation is inhibited. fixed support generates three unknown reaction components, two forces, Rx, Ry, and the one restricting bending moment. Determining three external reactions using the overall equilibrium equations is the first necessary calculation phase. Considering these boundary conditions, we have to determine the reaction forces, right? Once external reactions are found, we turn our attention to the internal mechanics using the concept of equivalent forces and moments. When a beam is loaded, internal stress is required to transmit the load along its length and maintain structural integrity. To calculate these internal forces, we employ the method of sections. We conceptually slice the beam at an arbitrary point x. In this case, we define the x-axis in this direction, and at x, starting from the left hand, we consider a section. Isolating by with this x isolating a segment known as a free body. So left part is now becomes a free body. At this cut section, the complex effect of the internal stress is often referred to as the distributed inner force is revealed. So if we cut in our brain, if we cut this part as a free body, in order to have the equilibrium of the forces and moment of this part, we have to consider an internal force distribution like this. All right. So by integrating all of this, we are able to define the the force to balance this force and this force. The key simplification is that we replace equivalently this continuous stress field with two resultant quantities acting at the centroid of the cross-section, centroid here, of the cross-section. We replace this distribution of the force. We are able to replace it with the force and moment. The force is called shear force because it is acting in the vertical direction in such a way. And also the actual force may sometimes exist. In this case, you are able to consider the horizontal component of this force. So in order to balance that component, we need the horizontal component of the force and x. And to balance the vertical component of this force and this, we need this. And in order to cancel the rotational effect of all of these forces, we need the moment to balance with it. These V and M vectors are essential because they must balance with P1 and P2, the external loads and support reactions acting on the specific isolated segment. All right. This simplification transforms the difficult task of stress analysis into the manageable application of static manageable application of static equilibrium equations to the free body. So if we consider this section, we have to consider only this force to take into account. But if you consider this section, you need to consider this force and this force on the virtual section. All right. So if you have multiple concentrated loads, external loads applied in the span of the beam, you have to consider several. You have to divide the interval, the bar length, into several intervals to consider these forces. A necessary prerequisite for correct internal analysis is the establishment of a consistent sign of forces and moments. Mistakes in sign convention are the most common source of error. For the internal shear force, B, we must define its positive direction relative to the free body cut. Let's consider the free body cut. This is a part of a beam. For normal forces, the positive direction of the forces are defined to be positive when the force vector is oriented to the external direction of the cut, like this. And the forces are in the direction to the body, it is defined to be negative. Okay, so this is quite easy. The standard convention dictates that internal shear is positive shear for shear forces case when the resultant external forces on the left side of the cut tend to push that segment upward like this. So this is positive. And relative, so it pushes up relative to the right end. So it looks like the rotation of a screw going forward like this. And if its effect is opposite, it is defined to be negative. So this is positive. If you look at the right side, then it goes down, and the left side it goes up. So this is defined to be positive. And the effect of this is giving such a phenomena when you consider a beam. Okay, positive shear force will give the downward bending like this. So you have to imagine a beam bent downward, like the bend of bridge or a string. Okay, the force, shear force, is defined to be positive in such a way. Similarly, the bending moment, positive moment is defined as the moment that causes the segment to deform concave upward like this. Okay, in this case, the moment is defined to be positive. Please memorize this image. And this shape is called sagging, and the opposite image is called hogging, just like the back of a pig. This curvature implies tension on the bottom surface. So when the beam has a tension on the bottom surface and compression on the top surface, then the moment acting to the part is defined to be positive. Okay? Adhering strictly to these sign conventions for both shear and moment is crucial when writing the equilibrium equations. The foundation of all static analysis is the application of the three equations of equilibrium. These equations ensure that a body remains stationary, neither translating nor rotating. First, we consider equilibrium of the forces. The sum of all forces in the horizontal directions must be equal to 0. Second, okay, this is the horizontal balance, equilibrium of the force components. Second, the sum of all forces in the vertical directions, y. Okay, I counts each force component. Must yi must also be equal to, the summation of yi must also be equal to 0. Okay? This and this are balance of forces. Okay, we are considering the beam case. Okay, so there's no z component in this case. And finally, the third case, we consider equilibrium of moment, the sum of all moments, okay, about any arbitrary point O. Okay, so when you consider this balance, you are able to consider any point to calculate the any center point to calculate the moment. Okay, and the summation should equal to 0. Should be equal to 0. We apply these powerful mathematical tools first to the whole beam to determine support reactions. We consider these 3, but not necessarily B3. Okay, you need only some of them to determine all the reaction forces and moment, reaction moment. All right. In order to understand the equilibrium, let us consider a free body of the cantilever beam that has already been shown previously. This is the free body that has already been shown. Let us consider a free body of the cantilever beam with the unknown actual normal force and vertical, okay, component, that is the shear force and reaction moment to balance with this force and this force. Okay. Take notice that all of nx, vx, and mx are assumed to be positive. Okay. By considering the equilibrium of the force in x and y directions and the equilibrium of the moment about the point on the right hand section, this point, to take the moment, okay, we obtain these 3 equations. This is the balance of force in x direction, and x should be the total, okay, sum of the x component of this force and this force, but there exists only x component of this force, so you obtain this. You need the sign alpha to decompose this into the vertical and horizontal components. Okay, so this is the balance of force equation in x direction, and in y direction, that is the vertical direction, Vx should be the sum of the vertical component of all these forces. So you have, okay, this will balance with P2 first minus this. All right, well, you are able to move this or this to the left hand side, and you can equate it to 0. All right, from that balance equation you obtain this. Okay, and the resulting moment mx should be the total moment calculated by taking the center here. All right, So mx should be p p p2 p2, and the distance is x minus a is this distance, so p2 x minus a, and you have to calculate the vertical component of this to calculate the moment. So p1 cosine alpha times the distance x. Okay, so you are able to obtain all of these three quantities by considering the balance equilibrium only. All right. But when you consider this section between this point and this point here, somewhere here, okay, somewhere here, and you are able to consider these quantities on that section, but there's no P2 between this point and the point between this and this. All right, so the horizontal component nx be the same as before, and Vx is different from the previous case because P2 does not exist in the free body when you consider between this point and this point. All right, and this horizontal component of this force only exists. Therefore, Vx equals minus P1 cosine alpha, this, and the moment is generated only by this force. Therefore, you have this, the second term of the uppercase. Okay, and you find that these reaction forces becomes functions of x. X is the variable, but you have to switch the range of the definition of these functions depending on the allocations of these forces. So take a look at the entire cantilever beam. But what is different is that the force at the left end does not have the horizontal component in this case. So in most practical problems, we encounter problems without actual force, normal force nx. In such cases, we have to deal only with shear force Vx and bending moment Mx. Okay, shear force Vx and bending moment Mx. The free body diagram depends on the number of vertical loads included in it. Therefore, the mathematical expressions of the shear force Vx and the bending moment Mx of the free body depends on the range of x. So you have to consider the range here and range here. Okay. In this case, for example, for the right section corresponding to x between A and L, here, between A and L, so this section, this part, we find both P1 and P2, in this free body, like this. We find Vx equals P2 minus P1 cosine of alpha, and Mx equals P2 x minus A minus P1 cosine of alpha times x. And for x between 0 and A, so this section, okay, this section, Vx becomes minus sine of P1 times cosine of alpha. Mx equals minus sine of P1 cosine of alpha times x. Okay, that this is a moment. Now let's consider a different loading, different from concentrated loading. This slide addresses the case of distributed loading conditions. In order to evaluate the total load, we have to integrate the distributed force. Okay, you have to integrate this distributed force in order to calculate the total load. In this simply supported beam, the total load is the integral of W, okay, W from 0 to L. Okay, take a look at this. All right. The reaction force at the end of A and B are the halves of this load. So you can divide the integrated load into two, so you obtain the reaction force here and here. Okay, this is symmetric at the center, so the total load is divided into two. WL over 2 and WL over 2 are the reaction forces at the end A and the end B. Okay, by considering the free body of the left part of the beam at X, okay, let's consider this part to calculate the reaction, shear force, and moment. Right. So for this case, you still have the distributed load like this, but it is equivalent to have the concentrated load at the center. So its value is Wx. Okay, integrating W from 0 to X, you obtain this as the concentrated load, equivalent load. Okay, so from this you can calculate the shear force, Vx. Vx equals this minus this. All right, and the moment is simply calculating the moment by this force and this force. So for this force, this force, simply calculate this distance x, and for this force, okay, you calculate x. You multiply x to Wx, you obtain Wx squared. Okay. Of course, the moment caused by the distributed load is replaced with the concentrated load like this. Okay, please take this in mind. All right. For considering the balance of the shear force and the moment, we can consider a free body taken from the right side. Okay, free body taken from the right side, not from the left side, like this. All right. This will give the same result. All right. And Vx equals W L minus X, but now X is taken from the right side. All right. So L minus X is the distance between this and this. Okay. Right. This is Vx, and Mx equals, you have to multiply. You have to multiply L minus X to this and to this. Okay. But in deriving this, please remember the sign of the shear force and the moment. And you may notice that if you differentiate this with x, with respect to x, you obtain, okay, if you differentiate of the moment, you obtain the shear force. Also in this case, if you differentiate this, you obtain this. Okay? It's very interesting. Okay? Therefore, moment can be obtained by integrating the shear force. Following the previous page's theoretical relationship, we derive a key application. Let us consider an infinitesimal part, like this, whose cross-section are in Mn left and PQ right. Okay, Mn and PQ right. Let us assume that both the shear force Vx and the bending moment Mx on the cross-section Mn are both positive as shown in the figure. Okay, let's assume like this. The cross-section PQ is away at a distance by dx from the cross-section Mn. So this distance is assumed to be dx. It is assumed to be very small. Therefore, it is natural to assume that the bending moment on this cross-section may change a little by dm. Okay, the moment on this cross-section would be mx, that is the moment on this section, plus the variation dmx. All right. Notice that because there is no external loading in this cross-section, there's no external load in this cross-section, in this case, to the path dx. The shear force on the right cross-section PQ should be, right cross-section PQ should be balanced with the shear force acting on the cross-section Mn. Okay. So there's no difference in Vx between this cross-section. Therefore, the shear force on the cross-section PQ should become Vx and mx plus dmx respectively. By taking the balance of the moment of this piece, we find, okay, mx plus dmx. mx plus dmx equals mx plus vx times dx. Okay, this mx plus dmx equals mx, this moment, plus vx times dx. And so this is its balance. Okay, mx equals mx plus dmx equals mx plus vx dx, from which we obtain, okay, by dividing this mx is cancelled out each other and this remains. Therefore, dividing the both sides with respect to dx, you obtain this, and this is a sort of differential equation holding between the moment and the shear force. Okay, that has you observed in the previous page in the actual expression of the shear force and the bending moment. Now we apply all the principle derived before to this example 1. This analysis starts by calculating all external support reactions using the overall equilibrium equations. Look at this figure. A simply supported beam is carrying a triangular shaped distribution of transverse load. At x, that is an arbitrary point, the distributed load becomes, okay, only at x, having the distance dx. Okay, let's consider this infinitely small distance. Then the distributed load becomes WL x over L. W0 x over L is the function of this triangle. So if you substitute 0 into x, you obtain 0, and if you substitute L into x, you obtain W0. So this is the function, and the function should be linear. This function is a function of this distributed load, and by dx is the width of the segment you obtain the force. So this integration gives the total load, that is W0 times L divided by 2. That is exactly the area of this triangle. Okay, that's the total load. And when you consider here, okay, this is the external load. Okay. So we can replace the distributed load with this equivalent concentrated load. In order to find its application point, okay, next question is, where does this force is applied? Okay, and it is not the center. That is different from the previous uniform distributed loading. All right, the centroid is a little bit right side from the center. Okay, you have to, let's calculate this distance first. The distance is assumed to be t, as you see in this figure. Okay, so in order to do that, you have to calculate the moment by this distributed force first. So this is the distributed force at x, and you have to multiply x to calculate the moment effect for this amount, and you have to integrate this moment from 0 to L2 to have the total moment about A. Okay, and let's assume that the equivalent concentrated load 1/2 times W0L is applied at a distance t from A. So the moment generated by this force is 1/2 times W0 times L times t. Okay, so this should this should be equal to this amount, and from this relationship we obtain this distance as 2/3 times L. That is exactly at a distance from distance L divided by 3, L by 3 from the right side. Okay, and this is the centroid part of this triangle actually. At the points A and B, only the reaction forces exist because the beam is simply supported and no reaction moments exist. The reaction forces are assumed to be Ra and Rb at A and B respectively. We can determine them by considering the balance of forces and balance of moments. In the present case, we can consider the balance of moments about A and B. Therefore, both reaction forces Ra and Rb can be determined by considering only the balance of moments A and B at A and B. The moment balance about B is shown here. Okay, this is the balance of moment about B. So the first term is the moment generated by Ra, and the second term has an opposite moment sign, so minus times this is the equivalent force to the integrated distributed forces, okay, times distance L over 3 equals 0, you obtain Ra. And Rb can also be obtained in the same manner. Now that we have obtained the reaction force at the left end A, we can consider a free body, that is the left part of X as shown here. Okay, this is a point A, and this is an arbitrary cross section located at X equals X. Okay, Because the length of this free body is x, the distributed load can be replaced with the concentrated load as the previous case. The distributed load value at the right end of this free body is W0 x over L. Okay, the shape is the same as before. Okay, the equivalent concentrated load is applied at x over 3 from the right end. Okay, x over 3 from the right end. All right. So the total load is 0. Okay, in order to calculate the area of this load, here you have W0 x over L, so you have to calculate 0 plus W0 x over L here. Okay, and you have to divide the summation with 2, and you have to multiply x to calculate the total moment. All right. So you have to multiply this, that is a total load, times x over 3 to calculate the moment, this. Okay. This is the total shear force, and this is the total moment by this distributed load. And this is the part corresponding to the reaction force, and this as well. The distributed load, okay, let's consider an arbitrary point y between 0 and x to calculate the moment. The distributed load at y is W0 y over L. Okay, y over L. Therefore, the total load is obtained by integrating this with respect to y from 0 to x. And this is the total loading here. All right. To find the point at which the moment becomes maximum, let's differentiate mx with respect to x. All right. You obtain this, and you find, just like before, this is exactly the same as the shear force distribution. By equating dmx dx equals 0, you obtain x equals L over square root of 3. That is the place at which the moment becomes maximum. By substituting this value into the expression of the moment mx, okay, let's substitute this into this, you can obtain the maximum value of the moment. That is this.